So I'm here to talk about two recent works. And the point is the study of graphs with prescribed mean curvature, typically CMC graphs and minimal. I will focus on those kind of graphs in product ambient spaces over manifolds with Ricci curvature bounded from below. This is a quite natural setting, but presents some analytical difficulties that I want to focus on in this talk. The talk will be split into two parts. The first one, I will present a Bernstein type theorem for minimal graphs. And the second part will be shorter. I will briefly talk about a splitting theorem for capillary graph, which is a kind of CMC graph with overdetermined boundary condition. So, okay, let us make the first switch. So I go to picture one. Okay, here is the setting. The setting is the following. Everybody does see correctly all of the screen? Is that okay?
Yes, okay.
It's okay? Okay, the setting is the following. I have a complete manifold, Riemannian manifold M with a metric sigma of dimension bigger or equal than 2. And I have a function U that creates a graph in R cross M. The graph map is phi, and I write sigma to denote the graph of phi. So it's a subset of M cross R. M cross R can be endowed with various different metrics, and the problem is particularly interesting when we endow. This slide should be read at top left, down left, then I'll show you, then top right, down right. If we endow the ambient space M bar, which is R cross M, with the product metric, so the R direction is parallel. And the sigma is endowed with the induced metric, which I call G, which is the pullback of the metric via the graph map. And so sigma can also be seen as the manifold M with another Riemannian metric given by the pullback by phi. So sigma and M are the same topological manifold with two different metrics. When I have an immersion of this kind, the mean curvature is the derivative, is a trace in the graph metric G of the derivative of the normal vector. And I took the choice that H is the derivative of the normal vector is minus the derivative of the normal vector in the upward direction. So it's a mean curvature in the upward direction. Okay, right. Let's go back and let's go to slide one. Minimal and constant mean curvature graph are the Euler-Lagrange equation of the area functional. So I make the graph vary a little bit in a compact region omega, and I measure the area of these variations that are compactly supported in omega, and H equal to 0 is the Euler-Lagrange equation for stationary points with respect to all variations supported in omega, and H equal to constant is that with respect to variation that are volume preserving in omega. If we write down the mean curvature written with respect to the original metric on M, it turns out that the mean curvature satisfies a quasi-linear partial differential equation of that kind, divergence of du divided by the square root of 1 plus du squared equal to H, where the gradient and divergence are the gradient and divergence of the original metric on M. So the metric for which M is a slice, not the graph metric. Okay? Right. The first result is a Bernstein type theorem for graphs which are minimal. And I start recalling the main achievements in the case the underlying horizontal manifold is Euclidean space. There are three. This first part of the talk will contain a lot of open problems that I believe be very interesting. Some of them are really challenging. I first detailed the following three results. The first one is the famous Bernstein theorem, and that says that all solution of the minimal surface, minimal hypersurface, as should be, minimal hypersurface equation are affine if and only if the dimension of the base manifold is at most 7, of the base Rm is at most 7. This has been a long journey, starting from Serge Bernstein in 15, beautiful proof, very non-trivial proof for dimension 2, and Fleming gave the first proof in dimension 2 that it allowed for extension to in the higher dimensional setting in the first 60s, and since then, in few years, with works of de Giorgi, and Simons, the Bernstein theorem was proved up to dimension 7. Each one is a big work in itself, and Bombieri de Giorgi just provided the first counterexample in dimension at least 8. Then Leon Simon provided many other examples. So, and the problem gave rise to a whole set of new techniques that favor the flourishing of geometric analysis. What happens if the graph is constrained? If the graph is positive, then actually positive graphs are constant in any dimension, not only in dimension at most 7. Okay, solutions are affine. That means they are a affine function that gives rise to hyperplanes in Euclidean space. Okay, concerning Bernstein 1. And also, the second result is due to Bombieri, de Giorgi, and Miranda. It followed the original Bernstein theorem, 69. So it's the same period, but slightly later. And the third result is tightly related to the second one: solution to the minimal surface equation on Euclidean space that grow at the most linearly are affine. Actually, if they grow at most linearly, they have bounded gradient, and this has been showed by Bombieri, de Giorgi, and Miranda. And if they have bounded gradient, they are affine by works of Moser and de Giorgi. And concerning minimal surface in minimal hypersurfaces, there are many open problems, even in Euclidean space. And I underlined the following conjecture on Leon Simon: every solution of the minimal surface equation grows polynomially at infinity. So there is a certain power such that a solution U of x is at it as most constant times R of x to the power q at infinity for some q. Okay? And this is open in full generality. What happens in the hyperbolic space? Because we want to understand for which kind of results, for which kind of manifolds, those results could still hold. And in the hyperbolic space, the picture is completely different. You know that the hyperbolic space can be written as the Poincare model, so a ball that has a boundary at infinity, and actually for every boundary data at infinity, there exists a solution of the minimal surface equation on HM, that means over HM. So for which the slide in M cross R is HM. So the ambient space is HM cross R, such that the boundary value is attained continuously in a suitable topology. And this is due to Nelly and Rosenberg and the Spirito Santo for Nari and Ripoll in higher dimension, Nelly and Rosenberg dimension 2. And it's quite recent. This has stimulated an interesting research in the last years, starting from reported Shevsky, and soon after, the group of Casteras, Holopainen, Ripoll, and Heinonen, in various combinations, made various interesting works to underline when the problem is solvable on a Cartana-Hadamard manifold that is a simply connected manifold with non-positive sectional curvature. Each of these manifolds is topologically Euclidean space, And it can be seen, it has a boundary at infinity appropriately defined. It can be seen that the problem is solvable if the sectional curvature does not approach zero too fast, but it is also pinched. So a one-sided bound in many cases is not sufficient, but the picture is subtle. Okay? So negative curvature basically gives no hope to have results of the type Bernstein 1, Bernstein 2, and Bernstein 3. So the question is, for which classes of manifold properties analogous of these three may hold? And an interesting class of manifold to investigate is that of manifolds with a non-negative Ricci curvature. Why? Because on manifolds with non-negative Ricci curvature, there is a well-established convergence theory initiated by Chigger and Colding that is in the same spirit of the theory used to prove the original Bernstein theory. That, however, needs further ingredients, but some of them are present for manifold with Ricci non-negative, and because there is an analogy with the theory of harmonic function on manifold with non-negative Ricci curvature. And indeed, if we see the function u as a function on M endowed with a graph matrix, so on sigma, u is harmonic. But you lose a control Ricci non-negative on the graph. What about the three problems? Well, problem one is completely open. As far as I know, there is no attempt to address the Bernstein theorem in full generality on manifolds that are not Euclidean space, even for sectional curvature non-negative. There is some result for asymptotically flat manifolds due to Carlotto. But in general, the problem is completely open. Property Bernstein 2 holds if Ricci is non-negative, but under a further assumption on the sectional curvature, and is due to Rosenberg-Schulz's proof in 13. And this is what we wanted to talk about in this talk. And problem 3 has been addressed by Ding, Yost, and Xin. If the manifold is has non-negative Ricci curvature and further assumption, maximal volume growth and quadratic decay of the curvature tensor. The outcome is a theorem that says that if you have on this manifold a minimal graph, an entire minimal graph that grows at most linearly, then the manifold is Euclidean space. But it's quite delicate. Okay. The problem B2 and B3 are very much related and can be addressed by similar techniques. B1 is much harder. And this is the theorem I want to talk about in detail. If M is a complete manifold and only under the assumption that the Ricci curvature is non-negative, then positive minimal graphs over M are constant. And this has been independently proved by Ding with completely different techniques. Entirely different approach. His approach is more technical in many points, and allows for extension to not necessarily to manifold with Ricci non-negative. You need to satisfy a volume doubling and uniform weak Neumann Poincare inequality. Okay, but the proofs are completely different. I want to focus on the proofs of B2 in the literature. They're available in the literature. So Bombieri, De Giorgi, Miranda, and then Rosenberg-Schulzen's proof. They are both based on local gradient estimates. So we suppose that U is a solution on a ball of the minimal surface equation and that it's positive in BR. Well, Bombieri, De Giorgi, and Miranda proved the first gradient estimate in a higher dimension. This is in particular relevant in dimension bigger or equal than 3 because the case M equal to 2 has been proved before with different techniques. And Bombieri, De Giorgi, and Miranda found that the gradient is up to some constant Cj, only depending on the dimension, bounded in terms of the exponential of U divided by R. In dimension 2, it's interesting that the function square root of 1 plus grad u2 has a very neat bound and the constant is sharp. So really, you cannot bound the gradient by something that is not exponential in U. You really need an exponential. And what happens, what about the proof by Rosenberg, Schulz, and Spruck? They assume non-negative Ricci curvature and sectional curvature bounded from below by some constant on BR. Then they get a similar estimate with U square instead of U. Okay? If you globalize these estimates, so you assume that U is positive on the entire M, you can send R to plus infinity, and you can observe both in Bombieri, De Giorgi, and Miranda, and in Rosenberg, Schulz, and Spruck that the gradient is bounded. So what can be proved from their gradient estimate is that a positive entire graph has bounded gradient. So how the argument, what's the end of the argument that allows to conclude that U is constant? Well, U is defined on the entire manifold, and we assume U is positive or non-negative. So without loss of generality, we assume that the infimum of U is 0. Okay? So we let R go to plus infinity, and we get that the gradient is bounded. Now, the minimum surface equation can be written if you isolate write down the divergence and isolate the terms, can be written as a linear operator in terms of a matrix whose eigenvalues have the following behavior. Both of them are bounded from above, but they decay as the gradient goes to plus infinity. So the operator is in general degenerate elliptic, and that makes the difference. But if the gradient is bounded, A is uniformly elliptic. And if you have a manifold with a negative Ricci curvature and a uniformly elliptic linear operator, you have a uniform Harnack inequality. I think this is due to Selov-Koster. Was previously known, obviously, in Euclidean space. So the supremum of U is controlled up to a constant only depending on the dimension and on the bound on the gradient times the infimum. But the infimum is 0, so you prove that the supremum is 0. Okay? That's why U is constant. So it's a two-step. One is a gradient estimate that says that the gradient is bounded, and it's a local gradient estimate. And the other is Harnack inequality, which is in itself quite a remarkable procedure result in itself. Okay? Is that okay? Are you following? Because I just see my it's hard this way. It's my first seminar, online seminar, and I see the picture. I see the beamer. I don't see you. I don't see anybody of you. So I don't have any. It's okay. I don't have any clue of what's happening. So please.
So it's great. We are following.
It's okay. Okay, good. So we go to our gradient estimate. So what the theorem, the Bernstein theorem, will be a direct consequence without Harnack inequality of the following gradient estimate. We take a complete manifold with Ricci curvature bounded from below, and we take a positive solution of the minima surface equation on an open set omega. Now the open set is you need to impose two conditions on the boundary. Either U can be extended continuously on the boundary of omega and is constant on the boundary, which is a case that we will examine later. So this gradient estimate will be useful later. Or omega, the boundary of omega is not too messy. What this condition with the limit tells us. You take a ball in the manifold M, and you measure the area of omega inside of a ball of radius r. And the area of omega for some sequences of r should not go to plus infinity faster than a quadratic exponential. So it's really a mild bound on omega. Omega cannot wrap too quickly at infinity. Is that right? So think that manifolds of this kind with Ricci bounded below, the growth of the volume of balls is at most exponential if k is positive, or polynomial. So this is a quadratic exponential. Nevertheless, we haven't been able to remove this assumption. I'm not sure it could be removable. But it's not needed if U is constant on the boundary.
Luciano?
Please, okay, please.
One question here of the tongue. The question is the minimal graph stable?
Yeah, minimal graphs are always stable, yes. And they are also calibrated. So they are also area minimizing, globally area minimizing, because we are talking about global graphs.
Okay.
I will use this fact later. Okay? Then the thesis is that the square root of 1 plus grad u square divided by e to the k square root of m minus 1 u is not bigger than the value of the boundary, the sup of the value of the boundary, the maximum between the sup of the value of the boundary and 1. So differently from the other gradient estimate, this is not a local gradient estimate. This is a gradient estimate stated in a form of a maximum principle at infinity. The set omega can be an open set, typically it's non-compact because otherwise there's nothing really, everything trivialized. The set is non-compact, and you are saying that either you attain the maximum on the boundary or you are still bounded by a quantity 1. So it's a maximum principle at infinity in the form of the maximum principle theories of Cheng-Yao and then Pigola, Rigoli, and Setti, and so and in a series of works. In particular, if omega is m, the boundary condition is vacuous, and you have this nice estimate, clean estimate. What about the sharpness? I just tell you in a second. I want to make a comparison with the case of harmonic functions. Our estimate is that square root of 1 plus du square is less or equal than e to the k square root of m minus 1 u. And in the case of harmonic function, you have this beautiful estimate that is due to Cheng-Yao, and then Li Wang cleaned the constant, and in the and du grows linearly with u. The estimate by Li and Wang is really sharp. That means if equality is attained at some point, then you are in a specific warped product in the case k is equal to 0. In our case, if equality is attained at some point, then k is 0 and u is constant. We are not able to find a warped product with negative Ricci curvature for which you can attain equality in these in our gradient estimate. And if you think about it, if in these typical examples the solution is 1D, and gradient Cheng-Yao's estimate says that u grows exponentially, but our estimate says that u blows up. So it's reasonable that you don't have really equality in the case k equal to 0, bigger than 0. You cannot reach equality. But we are not able to detail the case of approaching equalities, which are the models that approach equality. Okay? Hereafter, and I want to prove this theorem. Hereafter, we set w squared equal to the square root of 1 plus du squared. And I want to observe what's the strategy in Rosenberg-Schulten's-Pruck paper. That's the one that we follow most closely. The strategy is based on 2 points. First one, Jacobi equation satisfied by the inverse of W, which is actually the interior product with nu between nu the normal vector and the killing field dt on the graph. This is a linear PDE on the graph that parallels Bochner formula for the gradient of harmonic function. So Jacobi equation, it is Bochner formula for the gradient of the harmonic function u of on the graph. This equation has been is localized via the distance function on the manifold by using a method that is due to Korevar. And Korevar's method is similar to the method used by Cheng and Yao for harmonic functions. Okay, but warning, though similar, these two methods have significant differences, and Korevar's method is to me at least, much more obscure. I should say that Pieri de Giorgi and Miranda used the Jacobi equation, and think that we were in '69, so it was at the beginning of the rise of geometric analysis, and were among the first person who computed some differential inequalities on the graph and not on the base manifold. And this was one of the tricks. However, they use integral estimates instead of localization and Korevar's method, because they can avail of a Sobolev inequality on the minimal graph in Euclidean space. And a Sobolev inequality is not available, is don't know under which condition could be available if the base manifold M has only Ricci curvature bounded from below. Okay? Maybe, I don't know whether if the Ricci curvature is from below and the volume is maximal of M, so a Sobolev inequality holds on M, whether it could hold also on the minimal graph. I think this is an open problem. It would give much progress on the understanding if it were true. I want to discuss the main analytical issues where the case of minimal graph is considerably more delicate than the case of harmonic functions. We start with the Jacobi equation for w to the -1, so we need to find an equation for w to be able to bound w from above, and the equation from w is better to be written in terms of an operator which is a weighted Laplacian instead of the Laplacian on the graph. Every computation now is on the graph. Okay, and if we want to estimate in L infinity w e to the -cu, where c is actually equal to that constant, but also the following computation works for every c bigger or equal than k square root of m-1. And z satisfies this nice weighted operator on the graph, bigger or equal than the square fundamental form times z. So I'm sorry, the Jacobi equation, I just comment on it. First line, the Laplacian is the Laplacian on the graph. The potential terms contains the second fundamental form, square, plus overlying Ricci of nu. Overlying Ricci is the Ricci curvature of M cross R, of the ambient space. But since the R direction is parallel and we are in the product metric, the Ricci curvature in the ambient space is simply the Ricci curvature on M applied to the projection of the normal vector. And if we assume that Ricci is bounded from below, then we precisely get the lower bound given by the expression for LG of W in the third line starting from the last one. Okay, this term m-1 k square w square minus 1 over w. And what's the major difference with the case of harmonic function? In the case of harmonic functions, the term, in this case, we don't have enough help by a refined cut inequality for the second fundamental form, because the second fundamental form can be rewritten as the Hessian of U, and U is an harmonic function. So a refined cut inequality holds and estimates the Hessian in terms of the gradient of the modulus of grad U. But if you rewrite everything in terms of W, the gain that you get is very small and is lower order, differently from the case of harmonic function. And this causes that we don't have clearly an equation that shows L infinity estimate for C, differently from the case of harmonic function. Okay, that's a technical issue. So the choice is to localize. We don't have a nice equation for which we can prove an infinity estimate, for example, by integral methods. So we localize. How Korevar's method work? You take W that you want to estimate, and you multiply by a cutoff depending both on the distance from a point and on U. Very well crafted. So it's delicate how to construct it. Eta is exponential, but it's delicate. So if we compute the Laplacian in the graph of this product, we need at some point to estimate the gradient of the distance function in the graph metric. But the distance function is a distance function on M, on the original manifold. And the Laplacian, where the graph metric is essentially the matrix A that I showed you before. So A has two eigenvalues that are bounded from above, but may decay. So the estimate for grad R is no problem. You estimate with dr. Actually, the eigenvalues are bounded above by 1. But the point that makes the thing difficult is that if you want to estimate the Laplacian of R, you have a matrix Gij that has two eigenvalues that go to 0, may go to 0 very differently, but an assumption of Ricci just controls the trace of the Hessian in the original metric. So how can you estimate the Laplacian of R in the graph metric just without an assumption on Ricci? You need an assumption on the sectional curvature to estimate precisely the Laplacian of R in the graph metric. That's the point where the sectional curvature enters. We want to avoid this point, and we want, and to this aim, we want to replace R with a different exhaustion function. Exhaustion function is a function also called proper function, a function that goes to plus infinity as you diverge in the manifold M. Okay, so we want to create a different exhaustion function, and we want to this aim we use potential theory. We use stochastic geometry. It's un palavrão. You know, we use some aspects of stochastic geometry that are related to maximum principles at infinity, but some new aspect. I want to focus on now on the. I go through the details of the proof to show which kind of equation shall ρ satisfy. So the point is that to me and to us, Korevar's method is quite mysterious. It's really something magical, and we tried first of all to clarify why it works. Okay, and I tried to present at this point a simplification of this method to underline which is the role of each constant appearing. So we start with a constant which is bigger than the threshold that we want to achieve, and define z equal to w e to the minus cu. So we want to prove that z is bounded from above. And we fix a tau positive, and we want to prove that the following set, that omega double prime, is empty. If we prove that the following that this set is empty, then the thesis follows by letting tau go into 0, and then the constant go into the right constant. Okay? Is that right? Please tell me whether it's okay.
Yes, it is.
Hello?
It's all okay.
It's okay?
Yes.
Okay. What time is it? What time is it, please? I don't have. Oh. Just 1 second.
4:37. Okay.
Sorry?
It's 4:37. But you may have all time you need.
Okay, 427. Okay, that's okay. That's okay. Okay. By contradiction, suppose this set is non-empty, and note that since there is a lim sup on the boundary, the closure of this set is contained in omega. We fix positive parameters, and we take a non-negative exhaustion on omega double prime. What does it mean? That the subset rho less or equal than constant are compact in omega double prime closure. Okay? Typically, the distance in M from a fixed point is an exhaustion, but we want to find another one. And we define Z0 in the following way. I just, it's not W e to the minus Cu, so it is slightly smaller than Z. We put epsilon rho in the exponential, and we subtract delta. So it can be written as W times eta. And observe that since U is positive, and rho is an exhaustion, e to the minus Cu minus epsilon rho goes to 0 at x goes to plus infinity. So if, because there is this delta, the upper level set where Z0 is positive is relatively compact in omega double prime. And for epsilon delta going to 0, you recover Z. So for suitably small epsilon delta, the upper level set obtained by replacing Z with Z0, which is smaller, so the upper level set is contained in omega double prime, is still non-empty. But now this set is relatively compact because we have used the exhaustion. Okay? And we compute on this set, on the graph over this set, we compute what is LG of Z0. And what we want to get, observe that this set, omega prime, is an upper level set. And it's relatively compact. So Z0 attains an interior maximum point. What we want to get is for suitable epsilon delta and epsilon prime, that LG of Z0 is positive on omega prime. So it contradicts the maximum principle at a maximum point. So we compute LG of Z0, and we need to estimate the Laplacian of the cutoff eta. Eta, observe that it's an exponential that contains Cu epsilon rho. So we compute the Laplacian of eta, and we quotient by eta plus delta, and it is a term C grad U plus epsilon grad rho square minus epsilon Laplacian of rho. Observe that the Laplacian of U is 0 because U is minimal. Okay? Now we apply Young inequality. Young inequality gives you a grad U square times C squared times a tiny constant, slightly smaller than 1, and you lose terms with grad rho times a constant which is 1 over epsilon prime. That might be very big. but it's multiplied by epsilon square. So now, if epsilon is sufficiently smaller than epsilon prime, so we will later choose epsilon prime and then at the end epsilon, we can say that the Laplacian of eta is no more than that positive quantity that's basically c squared grad u square minus epsilon Laplace of rho plus grad rho square. And we get, we plug into the expression for Lg of z0, and we get that long coefficient in brackets. Observe that on sigma prime on the graph over omega prime, W times eta plus delta is positive. So if we are able to get a positive coefficient in brackets, we are done. So the observation is that it suffices that the Laplace of rho and grad rho are bounded jointly and not separately, like in the case of the distance function. So you have a PDE that rho shall satisfy. Suppose that we are able to find a function of rho that satisfies such a PDE on the larger set. So the sigma double prime is the graph over omega double prime that was the original set before using the exhaustion of rho. Suppose that rho is found. So the last term in brackets is less or equal than is bigger or equal than minus epsilon. And you get this equation. But now on the upper level set, grad u square can be written as w squared minus 1 over w squared. Recall that w is what we wanted to prove, to estimate. Z is what we wanted to estimate. So consequently w. But w is bigger than z, and z is bigger than 1 on this set. So grad u squared is at least a fixed quantity, tau. So we put, and if epsilon prime is small enough, since c is bigger than k square root of m minus 1, the coefficient of grad u squared can be positive. So at the end, we get an equation, an inequality that for epsilon sufficiently small, depending on epsilon prime and tau again, is positive on omega prime, and you get a contradiction. So the main point is that the Laplace of the exhaustion and the gradient of the exhaustion can be estimated jointly and not separately. So we can hope to find the equation. We want to find exhaustion satisfying this inequality and non-negative and going to plus infinity. Well, actually, if you exponentiate, you get a better inequality, simpler inequality. Laplace of v less or equal than v, and v an exhaustion. Okay, how to produce v? Now we want to produce this exhaustion. That's on the set sigma double prime, which is a smooth set. Recall that sigma double prime is the graph over omega double prime, which is an upper level set of Z and has compact closure in omega. And regular upper level set, we can choose tau such that everything is smooth. So sigma double prime satisfies three nice properties. It has compact closure in the graph sigma. No, not compact closure, sorry. It has closure contained in the graph sigma. The boundary is smooth and it's complete in the induced metric. And also bounded subset of sigma have compact closure, of sigma prime have compact closure in sigma. And these three topological properties, so sigma prime is an upper level set of a smooth function, so it's not too bad. Sigma double prime is not too bad as a set. And the first lemma is that if sigma prime in the graph satisfies these three equations, that sigma prime up to the boundary can be isometrically embedded in a complete manifold of the same dimension whose volume of balls, the manifold is called NH, the volume of balls of this manifold are not bigger than the intersection of the graph with balls in the graph metric in sigma prime. That with balls in the graph matrix of sigma prime, up to some constant 5 pi or whatever. The balls in BG is the ball, geodesic ball in the graph metric, centered at some point of sigma prime, P of sigma prime. And BH is a ball in the manifold NH, centered at the image of sigma prime of P via the isometry. A drawing, this might be a little bit confusing, but the drawing is very simple, and the drawing is this one. No, the drawing is this one. I hope you see it. Okay. So we have on the right here, we have our manifold M. This region is omega. The graph over omega is all this sigma, and inside of sigma we have a sigma prime. How we construct this manifold M? We basically double sigma prime. So we take a copy of sigma prime, abstract copy. We take a tubular neighborhood of sigma prime that gets tinier and tinier as you go to plus infinity. You construct a warped product matrix suitably on this shaded region in such a way that the lower part of the shaded region is totally geodesic, and you double. And you can control the volume of this region. And if you write down the metric appropriately, the warped product appropriately, the metric is complete. Because sigma satisfies those properties, in particular, the boundary of sigma is complete, and the bounded subset of sigma has compact closure, of sigma prime have compact closure in sigma. I wrote sigma prime should be sigma double prime, slightly larger, but the picture is the same. So we join two copies in this kind of dolphin's mouth. And you construct a complete manifold whose volume is controlled by the volume of the piece of the graph. The reason for this will be clear in a moment. We might be not clear at this point. Okay, so we double the manifold and find NH. And the second lemma is the following. So I'm sorry, I go back. So we can estimate the volume of a ball in our complete boundaryless manifold. This complete manifold NH has no boundary, in terms of sigma prime inside a ball of the graph. Okay, in terms of balls of the graph sigma prime. And how to estimate balls on the graph? The graph is calibrated. The graph is calibrated, and I show you what does it mean briefly. So the balls in the graph are estimated in terms of curvature of the ambient manifold and the behavior of the boundary. So the second lemma is take a complete manifold whose Ricci curvature decays not faster than at infinity. Very mild assumption, can be weakened also. You take a graph with bounded mean curvature, not necessarily constant, and you take the subgraph over a subdomain of the kind we want. Assume that the graph over this subdomain satisfies 1, 2, 3. So it admits a double, it admits an embedding into a kind of its double, okay, with controlled volume. If either of the properties of the boundary hold, then the manifold that we construct do not grow fast as balls that do not grow faster than a quadratic exponential. Let me just switch to this one. This is the picture. I think I can make 80 or 90. What does a calibration method mean? We have the graph sigma. Okay, we take a point which is an origin in M and a point on the graph P. We want to estimate the portion of P inside of a geodesic ball in the graph of radius r. Well, this is controlled by the portion of sigma inside a cylinder, the portion of sigma inside a cylinder that is written this way. On the base manifold is BR. And in the R direction, it's an interval. It's an interval that I call IR, that it's basically threshold of P, U of P minus R, U of P plus R. Now, on this subgraph, you have a vector field with zero divergence. That is called a calibration, because the normal vector field to sigma can be extended in parallel directions on the entire region, on the entire Euclidean, on the entire space, actually. So you integrate on this shaded region the fact that the divergence is zero. So what happens? Then the total flux is zero of this vector, and the flux over this boundary is the measure of sigma. And so you can control the measure of sigma by the absolute value or by the flux over these three regions, 1, 2, and 3. Now, what is the measure of sigma? Sorry, the measure of sigma inside of the cylinder CR. CR is the name of the cylinder, BR cross IR. A1 is the boundary of the ball of radius r inside of a manifold with quadratic decay of the Ricci curvature. So A1 grows like a quadratic exponential. A2 is the volume of a ball inside of this space, is a quadratic exponential. A3 contains a portion of the boundary of omega cross ER. So it's basically a quadratic exponential by our assumptions on the boundary. And if U is constant on the boundary, this term here has negative flux. Or if it has positive flux, you take this shaded region, on the other hand, to get it a term with negative flux. So you can get rid of this if U is constant on the boundary. In any case, you can estimate the area by these three areas, and none of them grows faster than a quadratic exponential. That's why you get an estimate for the volume of H, by a quadratic exponential, by the previous lemma and then a calibration argument. Okay, why quadratic exponential is important? Because of this result. If you have a complete manifold with volume growth not faster than the quadratic exponential, then you have a maximum principle at infinity. In terms of these, written in terms of this Liouville property. Any bounded subsolution of Laplace of W or Laplace of omega less or bigger or equal than lambda omega for some lambda positive on the manifold N, even weak solution that is bounded and non-negative, does vanish identically. Okay, this is a characterization first provided by Grigorian. Is actually one of the many characterizations of the stochastic completeness of a manifold. That is the fact that the Brownian motion, the trajectories of the Brownian minimum positive Brownian of the minimum Brownian motion on N have infinite lifetime almost surely. It's also said to be the known explosion of the Brownian motion. There are plenty of equivalent conditions focusing on different aspects of the stochastic completeness. One of them is this, and another is the famous weak maximum principle at infinity by Piccolo, Rigoli, and Setti. Okay? And the main point I want to show you is, how to construct, out of this Liouville theorem, I want to construct the exhaustion. And that's one of the main points. That is 1, 2, 4 here. This should be read from top to bottom, differently from the other papers, from the other. Okay, is okay. How to construct the solution is a very simple construction in this case. How to construct the exhaustion? We construct, since we have embedded sigma double prime isometrically in N, the exhaustion will be constructed on N. So we avoid stuff with the boundaries and so on. We take an exhaustion of N by means of relatively compact smooth open set. So each one has compact closure in the other. The union is N. And each one contains, I take a tiny ball inside of the first one. And on each omega uj, we solve a problem, getting a solution omega j, the following problem. Laplace of omega j is equal to omega j on uj minus b with boundary values 0 and 1. We extend omega j with 1 outside of uj, so you get an extension of this kind. You lose equality in the equation, but you still have inequality in the weak sense. It's simpler to see it in the viscosity sense, but it's also in the weak sense. So you have inequality for omega j on n minus b. Now, omega j plus 1, here is uj plus 1, and by by the maximum, by comparison principle, omega j plus 1 is below omega j. So the sequence of omega j converges from above, locally uniformly and locally in C2, to a solution of Laplace of omega equal to omega on m minus b. So it's something that goes behind each of omega j. It's non-negative and in between 0 and 1, but it's a solution of equality with equality. Now we extend it with 0 on the ball, on the neck. So we get a subsolution, but we have a bounded subsolution on this manifold. So this is 0. So omega j locally converges to 0. Now, how to construct the function? You take omega j, for every j, fix a large index such that omega kj is less than 1 over 2 over 2 to the j on uj. And you sum up each of these functions. The operator is linear, so the resulting function is a super solution on n minus b. It's non-negative. It's bigger than each of them, but each of these w, each of these omega, is 1 after some point. So that means that the resulting series is an exhaustion function, is proper, goes to plus infinity as you diverge in the manifold. It is pinched to 0 in here, but that's not a problem. It's a super solution only outside of a ball, but it can be easily, first of all, you smooth it up with a technique because it's locally Lipschitz, you want it smooth, and there is a theory by Green and Wu, you can smooth it up, getting still a super solution. Then you can translate it upwards, modify whatever you want on B, then rescale, and you can produce the exhaustion on the entire manifold that is bigger or equal than 1. So it's really, this is not a problem. It's just play with V. So you have to, that's the way it is constructed. And this is indeed, it's very simple in this case, but the principle is general.
Luciano?
Please, okay.
More on question here from Marcelo. The hypothesis of the Ricci curvature being bounded from below is also for N?
Yeah. The hypothesis, look, that's the hypothesis on the Ricci curvature is always on M with the original metric. The graphs have no control at all on their curvature. What we can control on the graph is the volume. So the Ricci curvature, this quadratic decay of the Ricci curvature is on M, is made up to estimate those kind of, in the calibration argument, those terms which are the simpler one, that are either the vertical, that are related to the boundary of a ball in M, or the term that are the horizontal part, which is the volume of a full ball again in M. Okay, so you don't control the curvature in N. Every control on the Ricci curvature is only on in M. You don't control in the curvature on sigma, and so you don't control the curvature on N. You can only control volumes. Is that okay?
Yes.
Okay. Okay, what I want to observe is that the above construction is a very particular case of a general principle that we call Alford-Kazminski duality, and we started to work on it with I started to work on it with Daniele Valtort, and then since 2015 we have developed the principle. We have extended its validity to fully nonlinear equations, also to first order operator. The principle states the following, that for a large class of fully nonlinear elliptic operators, the following are equivalent. A certain maximum principle at infinity stating that bounded subsolution of the equation on open set attain the supremum on the boundary, and the fact, that is K Kazminski property, that there exist families of exhaustion that are super solution and go to zero locally uniformly. The fact that the Kazminski property K implies a Liouville property is another aspect of the Pragman-Lindelof method. Is also the same principle. Is the same principle. The point is that a Liouville property allows to construct this family of exhaustion. You don't construct it by series because the operator is nonlinear, but you construct it by stacking solution of obstacle problems. But the principle is the same. And the example of minimal graph shows that implication from Alford to Kazminski can be really useful, because the UV property can be proved by integral estimate, and then you can achieve the exhaustion that allows you to localize the problem to apply to other elliptic estimates. I don't know how much time do I have. 10 minutes? Kind of this?
Yeah, Luciano.
Okay.
Can be.
Just state something about capillary graphs. And I want to state a splitting theorem. So I switch again to slide 5. Okay, this is the setting. Again, it's a little bit messy. Okay. these differently from the other slides have to be read from top left, top right, small left, small right. Okay, so the setting is the following. What is a capillary graph? We take a complete manifold M bar with boundary. We consider an embedded hypersurface sigma that touches the boundary transversely, and a set U, open set U, which is this one, that may contain a portion of the boundary. And we assume that sigma divides U into two pieces. And we can consider the functional measuring the area of sigma inside of U minus a coefficient times the volume of the region below. And actually, this coefficient, if you write this coefficient as cos gamma, with gamma in between 0 and pi over 2, so it's a value in between 0 and 1, sigma is stationary for this functional, and a stationary point is called a capillary hypersurface if and only if it has constant mean curvature and constant angle along the boundary. The angle between the normal of sigma, of the boundary of sigma inside of sigma, which is this one, and the normal of the boundary of sigma inside of the boundary of M bar shall be constant. Okay? In particular, if gamma is pi over 2, cos gamma is 0, and you reach the free boundary hypersurface, free boundary minima hypersurface. Okay? Okay, free boundary means 90 degrees touching on the boundary. What happens in the case of graphs? So if you, in this case, the ambient manifold is n cross R, and we have a graph defined on a region omega of M, which is this region, that parallels the boundary of M bar. Okay? So omega is a piece of M bar. Should be, in this case, should be basically this set. Oh, didn't know I could do it. Okay. So now B is the subgraph of sigma, and sigma is capillary if and only if this holds. So that means it has constant mean curvature, it has zero boundary value on the boundary, and it has constant angle that reflects into a constant normal value. This is a overdetermined, divergence. This is equal to some h. There is an h here. Okay. So it is this is called an overdetermined problem, elliptic problem, and for the mean curvature operator, there is the literature is very lacking. So there's a lot of things to do to characterize those domains, and especially what we want to. Okay, what we want to find is a characterization result. What are the examples that we want to? So we want a rigidity result. The examples that we can state are the following, that are called the standard ones. The half space. In this example, our domain omega splits as a boundaryless manifold n complete cross 0 plus infinity, and the graph is linear. Okay. But for h, this is h non-zero. If h is non-zero, we have the slabs and cylinders. So omega still splits as n cross 0t for some bounded interval, and u is 1d, and it's a circular. So these are pieces of cylinders. These are the other standard examples. Why not complete half cylinders? Because all of these examples that I wrote are monotone in the direction of the killing field. The solution is monotone in the direction of a killing field on the ambient manifold. So our goal is to prove a theorem that states the following: if you have a certain domain in a manifold with a lower Ricci bound, that it's reasonably well behaved, then and supports a non-trivial solution of a capillarity equation, so this overdetermined boundary value problem, then the domain splits and the solution splits. So this is one of the standard examples. That's the goal, and that's of this final part. We want to characterize capillary domains, so domains supporting a non-constant capillary graphs with non-negative Ricci curvature. And as I said, the standard example possess a bounded killing field in direction orthogonal to n. So the bounded killing field is also orthogonal to n, which it's orthogonal to the boundary. U is increasing along the flow, and U is bounded from below, but not always from above. The example of the half space shows. I just need 2 slides. What are our assumptions? Unfortunately, but in many points, we need manifolds with small growth. So in which sense? In the sense of potential theory, again. So we say that a manifold with boundary is parabolic if for some compact set with non-empty interior, the capacity of this compact set is 0. The capacity is defined in the very same way as the case of non-compact, as the case of boundaryless manifold. Observe that the test functions are not required to vanish near the boundary. So that's why the boundary is taken into, it's a Neumann parabolicity, okay? Facts: if you have a parabolic manifold without boundary, every subset with boundary, smooth boundary or whatever, we always talk about smooth boundary, is parabolic, okay? By the very definition, okay? Restricting every compactly supported Lipschitz function on M to omega bar. And we have the same classical condition, volume growth condition. If the area of omega inside a ball does not grow faster than quadratically, now quadratically r to the square, then the domain is parabolic. Okay? And here is the theorem. Take a complete manifold, and we take a connected open set with parabolic closure. We assume that the Ricci curvature is non-negative on M. This can be weakened. It needs to be non-negative on omega and needs to be bounded on M by a quadratic, something decaying quadratically. We take a solution which is C2 up to the boundary is smooth, C2 up to the boundary, non-constant on the boundary. Sorry, no, this is a, yeah, sorry. It's bounded, the function is C2 up to the boundary, is non-constant because otherwise the problem trivializes, and it's bounded on the boundary and solves the problem. So it has CMC and U, and the partial derivative are locally constant on the boundary, okay? Let me just, no, I'm sorry. On the boundary, they have to be locally constant, but globally bounded, both U and the eta U. I'm thinking about if the boundary has infinitely many connected components, the boundary value of U should be uniformly bounded and the boundary, the normal derivative of u should be locally constant and uniformly bounded, because otherwise it's really in a could be a trouble. And the infimum of u is bigger than minus infinity. We assume two things. Either u is constant on the entire boundary, or the boundary does not grow faster than a quadratic exponential, the area of the boundary. It's a mild assumption on the boundary. And this is a little bit more binding. We need the existence of a killing field on omega bar, which is transversal to the normal, to the data on the boundary. This is an explicit condition because du is the normal derivative. The normal derivative is prescribed. That means if the normal derivative in the outward pointing direction is positive, u goes upwards coming out, and sigma and x should go outwards to keep this derivative. So this is coherent with the standard example. It's a necessary condition to be a standard example. Under this condition, omega and the function u is a standard example. Okay, that's why. Just a couple of words to comment on how the proof works. The main point is that under this condition, infimum of u bigger than minus infinity, u and the partial derivative of u locally constant, we have an analogous gradient estimate than the one that I showed you for minimal graphs, for CMC graphs, that shows you that the graph of u is globally bounded. In our assumption, and we need also the boundary assumption, we have bounded gradient. So a solution that is bounded from below with a reasonable boundary condition has bounded gradient. If it has bounded gradient, since the killing field is bounded, one can prove using the parabolicity of the manifold. The parabolicity of the manifold reflects into the parabolicity of the graph, and this relation can be showed to imply that x grad u is positive on the entire manifold, on the entire omega. That means u is monotone in the direction of a killing field. This is usually a hard task to prove, and it's known only in few special cases in overdetermined problems, like in work of Beresticki, Caffarelli, and Nierenberg. In our case, we prove monotonicity via parabolicity method. Once we have monotonicity, to get the splitting, we resort on an integral formula. And the main point is that in this integral formula, like Schoen-Yau's formula, in this formula, the boundary terms vanish identically because of the overdetermined boundary condition. This is a truly remarkable point that has been observed for the Laplace equation by Farina and Valdinoci in a paper on ARMA, and we showed that the same phenomenon holds in our case. That allows to apply to use this integral formula with suitable test function and show that the Hessian of u has certain properties that imply the splitting. Some topological care has to be made. It's not immediate. Even the topological splitting is a little bit delicate, but it works along this line. So this concludes what I would like to show. And thanks. And I apologize. I think I ran out of time